you can have a quick look, you'll see this is the screen, so
Yeah.
you can kind of
I can move this to wherever you're.
Where do you
want this?
So that I'm not blocking this, I guess.
Yes.
So if you're off to the side.
Do you prefer the right or the left side?
I think here, yeah.
Yes,
Left
it's
side.
right.
Okay. Okay. Looks good. Try to stand somewhat close to the. So there you're not blocking at all.
Yeah, that's perfect.
That's a perfect place.
Oh, yeah.
Tilt it up a little bit more. Get more of this.
Yeah.
Are you ready?
Yes, it's now it's on.
Okay, there you go.
Yes.
Okay, so I'll just do a quick intro. So welcome everybody to the FPGA seminar for March, and today we have two talks from Jason Anderson's group, which are, I guess, rehearsals for date 2018 next week. So the first one will be Samriddhi Ansal and high-level synthesis of software customizable floating point cores.
So good morning, everyone. My name is Samriddhi, and today I'm going to be talking about high-level synthesis of software customizable floating point cores. This work I did over the past summer with Professor Jason Anderson and his group. So today I will be going over the motivation and methodology to building these cores, as well as some results that we obtained when we compared it to commercially available as well as open source cores. So first, let me start with the motivation for building these cores. As we all know, in high-level synthesis, we take a piece of code that's written in a high-level language, for example, C, and we turn it into a hardware circuit, as you can see here. And usually, now if you look at this C code, here you are performing floating point addition and division. And usually in high-level synthesis, floating point computations are not synthesized by the high-level synthesis tools. Instead, pre-instantiated floating point cores are just added to the hardware circuit. And the high-level synthesis surrounding circuit, which you can see in yellow, it has a knowledge of this interface and behavior with the floating point cores. So as you can see, there is a floating point core instantiated for addition and one for division. These cores are pre-written in Verilog or VHDL and are not customizable by the user, and unless you know in-depth hardware knowledge. So an alternative design methodology that was proposed was to specify the floating point cores in C and then synthesize them into hardware using high-level synthesis. The pros to using this method would be that the cores, since they're written in C, would be extremely easy to modify and tune to the application's needs. For example, using non-standard bit widths. Also, you do not need to worry about the IP core's interface with the hardware because it is synthesized along with the rest of the circuit, and hence it can also be optimized together with the rest of the application, and you don't have separate modules that your hardware needs to interact with. However, one of the big cons could be that it would be less efficient than the IP cores, because the cores which are written in Verilog or VHDL are highly optimized for what they do and tend to be much smaller in area and much faster. So in the process of generating these cores in C and generating them in hardware using high-level synthesis, we wanted to see that how good a performance could we achieve, and if so, what was the performance gap, and understand the trade-off between ease of use and customizability versus the performance. So keeping all this in mind, we went ahead and we created IEEE 754 compatible single precision floating point adder, subtractor, multiplier, and divider. So these are 32-bit operands. And so before we go into more detail about the course itself, I would like to give a brief overview of the floating point algorithm that's used, specifically the IEEE 754 standard. So floating point representation is very similar to the scientific form. As you can see in scientific form, we usually have a number which has one decimal and one number before the decimal, and it's raised to the power 10. Whereas in the floating point, you can think of it as being a binary number, which is the exponent is raised to the power 2. And so for single precision, or 32 bits, this is how you have a split in the 32 bits. The first bit telling you the sign of the number, the next 8 bits giving you the exponent, and the last 23 bits form the mantissa. Putting it all together, a normal 32-bit floating point number is as follows, where we have 2 to the power of e minus 127 times 1 point, and then the 23 bits of the mantissa. And I would just like you to note that this 1 is implicit. That means it is understood, and you don't include it in the 23 bits of your mantissa. Another interesting point is subnormal numbers. So this, the normal representation has a limitation that you cannot represent numbers which are smaller than negative 2 to the power negative 126. So in that case, we use subnormal numbers, where we have the exponent being fixed as 2 to the power negative 126, and the implicit 1 is now replaced by a 0. Apart from that, some special values that we need to take note of are plus and minus 0, plus and minus infinity, as well as not a number, which we have 2 kinds of, so SNAN and QNAN, the signaling not a number and quiet not a number. These special values have fixed, so in IEEE standard, they have a fixed floating point representation, which is unique to them. So for example, if you divide by a 0, a non-zero number with 0, you'll get an infinity, whereas if you add, say, infinity plus infinity, you end up with not a number. So all the cores that we generated in this study, including the RTL comparative baselines, so that is the Intel Altera cores, as well as the open source Flopico cores, they do not support subnormal numbers, and this just seems to be an industry standard. Now I would like to briefly go over the floating point algorithm for addition. So the very first step when we perform addition is that we check for special cases. That is, we check for zeros, infinities, as well as not a number. And this allows us to return a value very quickly. For example, if you're adding by 0, you just return the number itself. You're adding by infinity, you return an infinity, so on and so forth. Now, once that is out of the way, the next thing that we do is we check for the larger exponent, and we align the mantissa of the smaller number as need be. Then we go ahead, add or subtract the mantissas, and we normalize the result. Now I will go through an example explaining this algorithm in a little more detail. So the example that I've chosen, we have 2 numbers, x and y. X is 12.25 and y is 3.75. And these are the 32-bit floating point representation, where the red part is the exponent. And now putting it into more understandable form, we have x being 1.1 times 2 to the power 3, and y is 1.11 times 2 to the power 1. Now, as we can see, that neither of these are special values. They are both normal integers, so we don't have to perform any sort of special operation on them. As we can see, that the larger of the 2 exponent is of x, because it's 2 to the power 3, compared to y, which is 2 to the power 1. So now we set the result exponent to 3, and we align the mantissa of y accordingly. So by this, what I mean is that we adjust x and adjust y to both have the same exponent, which is a larger one, 2 to the power 3. And we do this by shifting the decimal point for y twice. Yeah. Now, going on to the next step, we just add the adjusted mantissas. And that's what we get as a resulting mantissa. Now, putting it all together, we have the result exponent being 3, result mantissa that we obtained from the previous step, and this is what we get as a number. However, this is not the standard form because our decimal point is supposed to be right after the first non-zero digit. So we perform a normalize. So in the normalize, we simply shift the mantissa by 1, and we add that 1 to the exponent. And putting it all together, we get 16 as a result. And indeed, x plus y is 12.25 plus 3.75, which is 16. Now that we have covered that, going on to multiplication, it is almost similar, except we will simply add the exponents, multiply the mantissa, and we normalize the results. Division is a little bit more complicated, and you can go through the division algorithm over here, but it follows the same first step where we check for special cases, and we do restoring iterative division. That was the algorithm that we chose to implement for our division core. So now I would like to talk about building of the actual core, as well as certain optimizations that we made in order to get the best performance for our cores possible. The first issue that we encountered was control flow. So control flow, when we would compile our cores using the LLVM compiler, all if-else statements would be compiled as branches. This would cause our control flow graph to be extremely branched and extremely large, as you can see over here. And because of this, it was very difficult to pipeline, and it was very difficult to essentially set it to accepting one input every cycle. So instead of using the if-else statement, we use the ternary operators, as you can see the question mark colon. What this does is instead of creating a branch statement, it creates a select statement in LLVM. And this allowed us to compress this giant control flow graph into one basic block. And this was very easily pipelinable. So as you can see, so that's over there. And that's how we were able to compress the control flow graph. Another interesting optimization that we made was using of the standard data types. We noticed that sometimes they would be wider than necessary. So what we ended up doing was using a tree-like structure with the nearest data type at each level. So for example, we started off, so this is a piece of code which is essentially does the computation for the number of leading zeros. We start off using an integer, and because we shift by 4, we make it then a short and then a char, so on and so forth. And this way we were able to optimize out additional area. The last interesting point that I would like to note is that we use bitwise operators, as you can see here, instead of using the logical operators, because sometimes the LLVM compiler would introduce control flow and we would use the logical operators instead of the bitwise operators. So all these allowed us to create very optimized cores. So if you're interested in finding these cores online and using them, you can find them at this link. And it is part of LegUp, which is a high-level synthesis tool, which is currently under development at the University of Toronto, and it is open source. So if you would like to take a more detailed look at the code, you can go there and find it. So next, I would like to talk about the evaluation methodology we use to test our cores. We generated 2 types of cores. The first one being LegUp 1, which were IEEE 754 compliant, and these handled special values. So by this, I mean that they were designed to handle infinities, zeros, not subnormal numbers, but infinities, zeros, not a numbers, etc. And then we generated a second round of cores, which did not include this handling of special values. So because of this, we were able to remove a large chunk of comparison code, and these legup 2 tends to be much smaller in area than legup 1. However, it is not IEEE 754 compatible. And this was because we were comparing it against two types of cores. First is the commercially available Altera or Intel PSG cores. These were IEEE 754 compliant, and they handle the special values. The second cores that we compared against were Flopico, which are open source cores, and these don't handle special values. So just to summarize quickly, we are comparing legup 1 against Altera and legup 2 against Flopico. Another thing to note is that we essentially created different design points by targeting different frequencies, and this is how we generated different latencies and area footprints. All of these cores are highly pipelined, and they accept one input per cycle. They are aimed at Quartus 15.0 as well as for the Cyclone 5 family. So now let's move on to the results that we obtained. So first I would like to talk about the adder. Now the area in blue is essentially where we want to be before that, let me explain the axes of the graph. So on the y-axis, we have our maximum frequency, or Fmax, and on so this is basically the speed of our core. And on the x-axis, we have the ALMs, and this can be thought of as the size or the area of our cores. So the area in blue is essentially where we want to be. The most optimized would be in this area, so that means extremely low area and very fast. So to go through the legend, we have the blue squares representing the Altera cores. The green diamonds is legup 1, which is with the exceptional handling. So these two are compared to each other. And then we have the orange cross, which is Flopico, and legup 2, which is the red triangle. These two are comparable to each other because neither of them do exception handling. So if we take a look at the graph, we can see that we tend to fall in the same ballpark as these commercially available graphs, as these commercially available and open source cores, which I think for something that is synthesized from C shows very promising results. Although, as expected, we do see that even our smallest core is 15% larger than Altera and 33% larger than Flopico, which is to be expected because it's not highly optimized. But in terms of speed, we do compare pretty well, with our fastest core being 19% slower than Altera's and only 2% slower than Flopico's. So that's the results that we obtained for the adder. For the subtractor, we obtained very, very similar results, which is to be expected because the algorithm that we used is almost identical to the addition one, with just a few tweaks to incorporate subtraction. And again, if you look at the results, we do fall in the same ballpark as the rest of the cores. And we are, again, just slightly slower than our addition core. So we are 5% slower than Flopico and 25% slower than Altera. However, for the multiplier was our weakest result yet. And to just take a look at the number of DSPs used, Altera is very optimized and uses only one DSP. Flopico uses 2, and the cores that we generated tend to use 3 DSPs. And so for some reason, the multiplier seems to be much less optimized, and even our fastest multiplier core was 41% slower than Altera's and 47% slower than Flopico's. For the divider, we did get some very interesting results. The legup as well as the Flopico cores, legup 2 and Flopico cores were very, very comparable, and legup 2 in fact outperformed Flopico, with our fastest core being 47% faster than Flopico, and our smallest core being almost 28% smaller than Flopico in terms of area. So for divider, when it came to Flopico and legup, we were very, very comparable, and in fact outperformed them. Another interesting experiment that we decided to perform with our with the same methodology was to make an arbitrary precision adder. And this is to see how easy it would be to create a non-standard bit width core and to check whether the performance and area would be comparable to Flopicos and Alteras. So this was also a test to see how easy it would be to customize the cores that we made. So we made another core which is called leg up 3, and it has a 10-bit mantissa, 4-bit exponent, and doesn't do any exception handling. Now, so the arbitrary precision adder, we see that there is a tremendous speed and area advantage, and this is compared to all of the reduced precision core relative to the single precision cores. This is because we had to do a huge number of checks to make sure that we followed the IEEE 754 standard, which we were able to remove when we were creating something with an arbitrary precision, the arbitrary precision adder. And this has a lot of applications in fields where you know exactly the amount of the bit widths that you need, and if you don't need all 32, you can create your own precision cores quite easily. And just to wrap it up, in the future we would like to make our own math library functions and explore the benefits of having these cores optimized along with the rest of the applications. So we want to check if it will allow for better scheduling and if there is any sharing of components. And so we would like to see that is the trade-off of performance as well as area efficiency worth the modifiability, customizability, and ease of use of this type of system. So I think depending upon the application, the user can decide which they would rather have, high performance and area, or if they want to be able to customize and use that customizability using our course. So, yeah.
Good. We have a couple questions. We take them now. Yeah.
Cool. I really enjoyed your talk. It's a lot of work for one summer, so
Thank you.
congrats. I guess in your methodology section, it's a little unclear of what benchmarks you used. So I was wondering, because I think depending on the application, maybe the placement tools might do different optimizations. So could you go into exactly what you did in your methodology?
So over here, the evaluation methodology.
Yeah. Yeah.
So essentially, what we did was what we noticed was when we looked at the Altera or the Intel PSG cores, they were completely IEEE 754 compliant. So this means they did all the exception handling, they did the checks for zeros, they would return QNANs, SNANs if you give them like wrong values or weird values. It was able to handle all of that. Whereas the open source cores or the Flopico cores did not do any of that exception handling. So it didn't handle if you gave it infinities, nans, none of that. So what we did was to compare against, so to have a fair comparison between the two, we created cores which did all of those checks, and we created a set of cores which did not do any of the checks, just to make sure that we were basically comparing apples to apples.
I guess what maybe didn't quite come through, which is, it's a good question, is that when you run Altera's core generator, if you've never run it, but probably, right? But if you run Altera's floating point core generator, for say just floating point adder, you can give it different Fmax targets, and you can basically sweep the Fmax, and it will generate cores with different numbers of pipeline stages and different area and different Fmax. So that's why we have such a wide array of points for the floating point adder from Altera. And then for leg up accepts a clock frequency, target. So by sweeping that, you can, from HLS side, also generate a range of, say, floating point adder implementations. So each of those benchmarks is sort of a different speed area variant by changing constraints on the core generator, either HLS or Altera. Does that make sense?
Yeah.
Sorry,
Yeah.
you.
And also to add to that, sort of you were mentioning applications, so all these results were synthesized in isolation of what application. We haven't looked into that, but if we now put these cores inside an application, there's more things to explore. Maybe some things can be shared. There could be co-optimization across these cores and the rest of your code. So that's not work that we present here, but it's definitely something interesting to look at.
Are these supposed to place in route maxes?
Yes.
And just another interesting point was that it was extremely easy to modify from leg up 1 to leg up 2. It was just a matter of commenting out that section of code that was doing the checks. So it was extremely easy to modify, as in compared to if you have to modify something that's written in Verilog or VHDL, if you go in manually, you know exactly what you're doing, and that tends to be really difficult. Yeah.
Okay. Good hearing. All right, so as Julie gets set up. So the second talk will be given by Julie Shao. It's called Sensei, an Area Reduction Advisor for FPGA High-Level Synthesis.
Keep on just getting set up here. Oops. Okay. So, thanks for coming to this presentation. So my talk is called Sensei, an Area Reduction Advisor for FPGA High-Level Synthesis. And the outline of this talk will be as follows. I'll talk a bit about the motivation, go into more detail about the framework that we propose and the different formulations, and go into briefly describe the evaluation methodology, show some results, and conclude with a few takeaways and some notes on our future works that we might want to explore. So first, the motivation. We all know HLS, it's great for you because it abstracts away a lot of the complexity involved and in generating hardware design, and it reduces the turnaround time for your design and verification for these hardware circuits, and reduces a lot of the effort involved in this. So this is very good, but one of the main concerns that people have is that these generated cores typically have lower performance or area efficiency than the manual design. And in this talk, we'll try to tackle on the area efficiency aspect, so we don't touch performance here. So with your high-level synthesis, your input is a high-level program, such as C, and these software typically use data types that are quantized in their width, so 8, 16, 32, or 64, versus in your hardware circuit, your data path can be of any arbitrary width. So on the one hand, these quantized widths are very good, well suited for standard processor pipelines, versus if you use it to describe hardware circuit, you get a lot of wasted bits, and that wastes a lot of area. So a lot of HLS tools these days have this sort of bit width minimization framework that allows the user to first specify a reduced width variable in their source code and have some kind of compiler optimization that will try to induce reduced width, either based on constants in your code or these user specify reduced width. So with that in mind, now your design methodology might look like this. You have your C program, you try to iterate, you try to go through your program and specify some variable as a reduced width variable. You get your modified C program that gets passed into the HLS tool, and you get a hardware circuit that has some area reduction, but this might not meet your area target that you're trying to aim. And you can go back and iterate through different variables in your program, try to squeeze out more area using this method. However, this is very time-consuming, mainly because you need multiple invocations of your downstream synthesis tool, which takes a long time. And you really need to sit down and think about which variable should I try, because there could be different area implications by reducing different types of variables. So we propose this design flow where we have this advisor, which we call Sensei, which will identify for you which variable has high area impact, as well as give you an estimate of the amount of area reduction you can expect from this variable. And you would take the advice from Sensei and modify your program accordingly, and you have this more straight line pass through your design iteration. So the main challenge for this work is in which variable to constrain in order to meet your area target. And this is hard because you have many variables in your C program, and the post-synthesis area impact of these of the C variables could be non-trivial because of many factors such as optimizations in your CAD tool. So we really need a way to accurately estimate and rank these, the area impact of these variables. And our framework Sensei tries to do that. So now I'll talk a little bit about how Sensei does that. So suppose you get your input C program, AES, just as an example here. Sensei will look at every single program variable inside your program, and for each of them, squeeze the width and generate a reduced width data flow graph based on that. And each of these graphs will get passed into a predictor. The predictor will predict the amount of area that you can reduce from each of the data flow graph. That all gets aggregated into a report, which is essentially a ranked list of variables and their area impact. And you as the designer will look at this report and modify a C program. So the main meat of this framework lies in this predictor, and for this work, we explore two different types, one analytical and one CNN-based, CNN convolutional neural network, very popular these days. So let's first look at the analytical approach. For this, we use a typical HLS approach where first we try to track the number of bits reduced per instruction type in your data flow graph, and also we try to profile an area reduction factor for each instruction type, multiply them together, and you get the area reduced for each instruction type, and the overall area reduced for your circuit would be the summation overall instructions in this method. And so while this looks simple, it actually naively assumes a linear relationship between the number of bits reduced and the area reduced. As well, it considers the area reduction in isolation and ignores a lot of the correlations between operations. And so this tends to result in an overestimation of area reduction, which I will show later in the results slide. So this is not so good. Let's see if we can do better in the CNN-based predictor. And for this, what we wanted to do is to be able to find spatially localized features and find some nonlinear relationships that are more data-driven in this predictor. So in order to build this CNN-based predictor, first problem we have to solve is how do we map a program's data flow graph into an image representation so that the CNN can understand. This is hard because the data flow graph for a program could be of arbitrary size. So in order to do this, we make the observation that if your area reduction is coming from squeezing a variable, most of the area saving in this circuit then will be relatively close to this source variable that you squeezed in the beginning. So based on that, we decided to just capture a window of your data flow graph centered around this initial variable that you squeezed down. So for this window, then we have sort of two parameters, the connectivity and the depth. So the connectivity means for a given node, what is the maximum number of edges you want to capture in its fan-in tree and its fan-out tree, so C-in and C-out. And the second parameter is depth. So for a given variable, how many layers do you want to capture? So also in its fan-in tree, D-in, and its fan-out tree, D-out. And these four parameters then will uniquely define the maximum number of nodes you can capture from your DFG, and also the image size you need. And so let's go through an example to make this a bit more concrete. Say you have this simple 4 lines of code. You get this data flow graph that corresponds to it, and you pick the parameters C-in and C-out equals to 3, D and D-out equals to 3. Then you get sort of an image that looks like this, where each square is a pixel, and on here I kind of merged some of the pixels, merged some of the squares together, and that just means the pixel value is repeated across those pixels. So say you want to reduce the width of variable D here, and what we do is we put variable D directly in the center row, and the top half of the image, then we use it to capture all the variables in the fan-in tree of variable D. So in this case, we see that variables C and B both contribute to variable D, so that gets placed in the row directly above. And we do this recursively, so we see that C is produced by A and B, and those get placed in here, line 1. And anything, and A and B, they're not produced by anything, so every other pixels in this upper half is left empty. And similarly, the bottom half of our image, we use it to capture all the variables in the fan-out tree of D. So in this case, we see that D is used to produce F, that gets placed in the row directly below, and F is used to produce G, which gets placed in line 5, in row 5. And so this dictates where we're placing these pixels, and what we actually put in the image is data, information about these variables. So one useful information could be its original bit width before you squeeze down the variable size. Another layer could be the change in bit width as a result of you squeezing down that initial variable. And of course, another one is the instruction type, which corresponds to sort of how big the final functional unit will be in your hardware. And so with this, just stepping back for a second to look at the whole picture, then this predictor will take the generated data flow graph, generate a prediction for each of them, and you can use it in your modifying of your C program. So for this work presented, the results, we use Cin and Cout equals to 3 and Dn and Dout equals to 5. And I'll talk a little bit about the reason behind these, but the main thing to note is that we just want the window to capture enough information so it can make some area prediction. And to do this, our rationale for Cin is that because each node is an instruction in LLVM, most of them have 2 operands, some of them have 3 or more if it's a call instruction, but we picked 3 to cover most cases. And for Cout, we profile the CH-stone benchmarks and looked at the distribution of nodes and looked at the number of fan-outs they have. And we see that with 3, we cover about 95% of all the nodes in a program. So we say that 3 is pretty good. And for the depth, again, we profile the same CH-stone benchmark and look at how many levels can you traverse until the beginning of the furthest node in your program. And as well, you try to traverse downwards in your data flow graph. And as you can see, this is a very large number. We kind of tried 2 different numbers. We tried 8 and 5, and we saw that 5 gave similar results in terms of accuracy as 8, and so we opted for that, just so that our image is smaller, and when we train, it's a lot faster. So that's the rationale for choosing these parameters. Of course, it's not super optimized. There could be more work, but this is what we used. So now onto the evaluation methodology. Because we're using a CNN, we need a lot of data. And what we did was we took the CH-stone benchmark and generated lots of data points from it. So for each benchmark in the CH-stone benchmark suite, we look at every variable and reduce their width to one of these numbers, and each of them would be 1 data point. And for that, for the synthesized part, we synthesize it to a Cyclone 5 device using U of T's LegUp high-level synthesis and Cortex 15. And so now we have all these benchmarks, or data points, and we need to divide it into 2 sets, the test set and the training set. So what we did was for each benchmark, we randomly picked 10% and assigned it to the test set, and the rest to the training set, which leaves us 640 test points and 6,400 training points. And we ran the whole evaluation using Caffe. We trained it for 1,000 epochs. And what we want to see for the predictor is how well it's able to predict and rank these 640 test points. So let's look at the analytical predictor first. So for this chart on the x-axis, I'm plotting the actual ALM reductions as reported by Cortex. And on the y-axis, I'm plotting the predicted ALM by the predictor. So in this one, the analytical predictor, as you can see, there are many overestimations of the area reduction. And also it's kind of all over the place. There's not something super easy to sort of normalize it to. So it's not very good, and it's mainly because of the reason I sort of mentioned before. It's unaware of nonlinear relationships, unaware of any interactions between operations, or any effects of the optimizations in the downstream synthesis tool. So now let's look at the CNN predictor. So in order to do that, first thing we needed to do was actually create a CNN model, because this is there's no really readily available architecture for this type of prediction task. So we actually went ahead and just try a lot of different simple architecture, around 200 different configurations of different number of convolutional layers followed by different number of fully connected layer, and we came to a conclusion for the best trade-off between the amount of time you need to train this thing and the accuracy you end up getting, that one convolutional layer followed by one fully connected layer gave us the best trade-off. So with this, I kind of just plotted it right beside the analytical predictor, and you can see visually it's doing a lot better. There's no obvious under or overestimation just by visual inspection. And that's try to put some concrete number to it. So for accuracy, we define the metric epsilon as an error threshold in terms of the percentage of the overall circuit area. And we want to plot the percentage of predictions generated by this predictor that are within this error threshold. And we sweep the error threshold from 0 to 1% of the overall circuit area. And here the black line is the analytical predictor, and the red line is the convolution or CNN-based predictor. And as we can see, if you're able to tolerate around 1% of error, then it's able to give you 87% of the predictions that it gives you are accurate enough. So that's on accuracy, how well it can give you an estimate of the amount of error reduction you can get. We also looked at how well it can rank variables. So what we did was we made the two predictors predict the best variables for each of the benchmarks. We take the top 5 candidates from each of the predictor and look at the actual ALM savings generate those top 5 corresponds to, and average them and put them on this bar chart here. So in the dark purple, it's the CNN base, and the light purple is the analytical. And as you can see, many of the points, CNN based are doing pretty well, and the ones that it's not doing super well, it's quite close to the analytical based one. And so that's the average. We also looked at sort of a range, the maximum and the minimum area reduction that you can get based on these top 5 variables. And for most of them, even the ones that where the average were pretty slightly less than the analytical, we can see that the best one it gives you is the same. So with this, we conclude that the CNN-based predictor is also doing very well in terms of its ability to rank variables. And on average, the CNN-based is able to give you 2.3 times more ALM saving if you follow the advice of the CNN-based predictor. So in conclusion, or in this presentation, we talked about Sensei, which is a framework that guides the HLS users in where to focus their efforts, and it identifies for you variables with very high area impact and provides you with an accurate estimate. And what this does is it really helps you eliminate the wasted area due to over-provisioned software data types, and reduces a lot of the time and effort spent on iterating through your design. And for future works, we want to expand this predictor framework to predict also the DSP and VRAM reductions, as well as sort of perform more of a detailed analysis on the different features that the CNN was able to learn. And of course, in this, we explore some very simple CNN architecture. There could be more work done in that front to make the results even better. And the last thing that we're interested in is to apply this to predict sort of error propagation and error predictions for things like approximate applications. And yeah, that's all for my talk. Thank you for listening, and I'll take any questions.
Is there any intuition into why you chose CNN as like your first, or was it your first your first machine learning algorithm you tried? And is there intuition why CNN and not like deep neural nets, like fully connected layers, or like an SVM or something?
So the main intuition kind of goes back to the observation where if you squeeze a variable down, most of the area savings you can get are going to be close to it, and because we formulate it in the way that you capture spatial locality, CNN was the candidate we chose. Yes.
How sensitive do you think it would be the results if you change the benchmark out of which you generated the training?
So, because it's more data driven, I think it should be okay if you, say in an industry setting and you have all these different benchmarks, then you would be training it on a large set of user design, which should cover all sorts of different benchmarks. In that case, the CNN should generalize. If you have a good enough architecture, it should be able to generalize. Here, we're not really able to explore that axis because of the limited time involved in generating these data, but
I'm just thinking that, I mean, there are different patterns, different in the benchmark. But if I train the network with the source code of different ciphers, for example, right? Like AES, all the different variations of ciphers, they more or less have similar patterns, and not so much perhaps more floating point patterns or something like that, and then maybe give you better training data, maybe.
Yeah.
Or how much it would impact, or maybe it's just detrimental, I don't know.
Yeah, that I'm not too sure, but if you know beforehand
Right,
that
exactly.
like which set, then you can just train on that set, and you would
exactly.
perform very well in that task. Yes.
Just a couple small questions that I enjoyed working at, but I guess the first one is, have you explored different rounding modes when you're reducing your bit widths?
Different rounding modes?
Yeah. So like truncating versus rounding up versus some sort of stochastic rounding mode.
So we haven't really looked at this. This work, we're not really. So the parts where we reduce the precision, it's supposed to still be accurate. We're trying to look for the ones that are wasted, so bits that are actually not used or are very static. Those we can get rid of. We're not trying to round your results or anything in this work.
Okay. And,
So we haven't explored rounding modes.
Cool. And one other one, and so this, again, this would probably explode your design space, but it looked like that you were reducing the bit width for every variable, right? But like, have you ever even explored about having different bit widths for different variables? Because some variables might be very sensitive to reducing bit widths, but in the same program, maybe another variable might not be, right? So
Yeah, so that's what I guess, that's what the predictor is trying to do. It's trying to sort of learn based on where it is in the data flow graph, because area sensitivity really relates to sort of how many variable it fans out to, what type of functional unit it is involved in. So I guess what was I gonna say? Sorry, I blanked.
Yeah. So that makes sense. Okay.
So I guess you'd have your sort of HLS tool. You'd have a trained neural network, right? And HLS, you're going to use that trained neural network to produce an ordered list of variables that the user should look at in terms of choosing bit widths for, right? And it's going to be ordered where the predictor thinks that's the most profitable one to look at the bit width of, right? As far as area reduction. So yeah, you would have your sort of HLS tool would have the program in memory and the compiler, and for every candidate variable that you want the user to think about reducing, you would do an inference for that. Does that make sense?
Yeah.
Okay, any other questions?
Just a quick question about the correctness. Once you start reducing bits, I guess the correctness is still left to the user to test and make sure that actually works.
Yeah, this shows you if you were able to reduce this is the potential you can get, but it doesn't tell you do this. It gives you a suggestion based on the ranking.
Great. Thank the speaker one more time. And you can smell the pizza. We would like